Today, we're going to be talking about the real number system. We're going to be filling in a graphic organizer to better understand the different types of numbers. Let's start by filling in this box in the center, the tiniest rectangular box. You're going to grab a text box. I'm using size 24 and I'm using the color green. I chose the color green because green makes me think of natural things like trees and plants. The natural or counting numbers include the basic numbers that you count with, like 1, 2, 3, 4, 5, etc. You get the idea. So natural counting numbers are simplistic. Now let's go ahead and make a new text box up here in the next box. And then I'm going to choose the color blue. And I'm going to change this to a size 36. And then the whole numbers, W, H, and then instead of O, the letter O, I'm going to type a 0. And the reason why I typed a 0 is because 0 is the only number that separates the whole numbers from the natural counting numbers. How this is set up is that this box right here encompasses the natural counting numbers box, or you could say it surrounds it. And that's because the whole numbers include the natural or counting numbers. What I mean is that these green numbers, 1, 2, 3, 4, 5, those are natural numbers and they're also whole numbers. The whole numbers, though, they also include 0. Now, natural counting numbers do not include 0. That's why 0 has to be in this outer box. Now make a new text box in the next section, and I'm going to use red because this will be the first time that we talk about negative numbers. The integers include numbers like, well, let me make another text box. -3, -2, -1, etc. And the integers also include 0, the whole numbers, and also the natural counting numbers like 1, 2, 3, 4, 5. So integers are not just the negative numbers. Integers also include 0 and 1, 2, 3, 4, 5, etc. We have to leave this negative on the outside though because whole numbers do not include negatives and neither do natural counting numbers. So integers are basically all the numbers besides numbers that have a decimal expansion or fractions. Let's become a little bit more creative with our idea of integers though. So I'm going to go to the drawing tool and I want us to think about the perfect squares and the perfect cubes. So let's take, for example, 25. I can actually write the square root of 25 in the integers box because the square root of 25 is equal to positive or negative 5. Basically, when you see a square root, you're asking yourself the question, what number multiplied by itself gives you the number under the square root? Or you could say, in this example, what number multiplied by itself gives you 25? Well, 5 times 5 gives you 25, but also -5 times -5 gives you 25. Remember the multiplication rules. Like signs, you get a positive. So that's why there's two answers. And 5 and -5 are both integers. Let's think about the perfect cubes now. I'm erasing that because we're going to need that space later. So let me go down to the perfect cubes and let's use 8. So let's say I recorded the cubed root of 8. Well, the cubed root of 8 is equal to 2. It actually only equals 2. We're asking ourselves what number multiplied by itself gives you 8. Well, 2 times 2 is 4, 4 times 2 gives us 8. it won't work for us to have -2 as the answer, because -2 times -2 is 4, and then 4 times -2 is actually -8. So the cube roots only have one answer, just the 2 in this case. I'm going to put one more cubed root in our integer section. So I'm going to use 1. And I'm going to write, I'm going to try to fit this, the cubed root of -1. The cubed root of -1 is equal to -1, which is also an integer. Now, the cubed root of -1 is only -1 because think about it. 1 times 1 times 1 is going to give you 1, not -1, so 1 is not the answer. Only -1. So you have to remember that the cubed roots only have one answer. See? But the perfect squares, when you take the square root of a perfect square, actually if you take the square root of any number but 0, you're going to get 2 answers. Well, that's not necessarily true. The square root of -1 actually equals I, but that is something we should get into in another video. Let's go ahead and move on to rational numbers because I'm starting to make integers too complicated. All right, so we write rational numbers, and then what we're going to do is we're going to click markup, and then I want to use the box highlighter, and I'm going to use yellow for my highlighter, and then over here, what I'm going to do is I'm going to highlight this word ratio. And I didn't talk about this the other day, I forgot to do so, and I wanted to make sure that I talked about it today. The word rational has the word ratio inside of it. So when you think of ratio, you should be thinking of 2 to 5, or 2 to 5, or 2 to 5, like that. The idea is that rational numbers are any number that can be written as a fraction. So this would include numbers like 1/2, which is already a fraction, 0.3, which can be changed into a fraction. That's a terminating decimal, so we would use place value to change it into a fraction. It also would include any repeating decimals. Remember, repeating decimals can be changed to fractions using the 9 rule or the algorithm. We could also write mixed numbers. We could include improper fractions. We can include, here, let's write a crazy number, -1000.1287334. That's a terminating decimal, so you can use place value to change it into a fraction. Let's write one more. Let's see if I have enough room up here. I'd like to write 0.142857 with a repeat bar over it. That number is actually equivalent to the fraction 2/7. So you could use the 9 rule and then reduce it all the way until it became 2/7. So basically what I'm trying to show is that rational numbers include any number that can be written as a fraction. Now, I want you to remember that this box surrounds all of these other boxes, the integer box, the whole number box, the natural counting numbers box, which means that integers, whole numbers, natural counting numbers are all rational numbers because they can all be written as a fraction. Think about it. 0 you can write as a fraction by writing 0/1. -3, you can write that as a fraction by writing -3/1. So all of those numbers in that box are rational numbers. Which brings us to the numbers that are not rational numbers. So I'm going to go back to my text box. I'm going to use the color black, and you'll see why in a second. I'm going to be highlighting, and this just makes it so that I can still see the original words. All right, irrational numbers, and then I'm going to go over to the markup tool, and I'm going to use red, and I'm just going to highlight the IR portion. And then I also wanted to highlight this word ratio. Let's see if I can do that. Okay, great. And then I'll go to my drawing tool. IR is a prefix, which means not. And then basically after that, we have the word ratio. So not ratio, meaning irrational numbers cannot be written as a fraction. So let's start with some examples of numbers that cannot be written as fractions. So our first example is pi. Pi is equal to 3.14. That's gonna bother me that we have a decimal in front. Let me fix that. 3.141592, etc. Another example of an irrational number would be e. E is equal to 2.718, etc. It goes on forever and it has no pattern. So an irrational number, when you look at the decimal expansion, it goes on forever and has no pattern. All right, now let's look at the perfect cubes and the perfect squares. Now, if you take the square root of a perfect square, you're going to get an integer, which is rational. But if you take the square root of a non-perfect square, you're going to get a number that is irrational. For example, the square root of 2. Let's type that into the calculator. The square root of 2 is equal to 1.41421356, etc. It goes on forever, and there's no pattern. And we know that I knew that this was going to be irrational because if you look at the chart, 2 is not a perfect square. 2 falls between 1 and 4. 2 is a non-perfect square. Let's come up with another example that we can record. How about the square root of 75? Well, 75 would fall between 64 and 81. It is not a perfect square. Whoops, let me undo that. So let me go over to the calculator and type in the square root of 75, and you will see that I do not get an integer. I get a decimal expansion that goes on forever and has no pattern. Now, the calculator doesn't show it going on forever. The calculator rounds, but just trust me, it goes on forever, there's no pattern. However, if you took the square root of a perfect square, like 36, you're going to get an integer. Okay, so we wrote the square root of 2. I was going to write down the square root of 75, and now I'm going to move on to the perfect cube numbers. If you take the cube root of 64, you'll get 4. If you take the cube root of 216, you'll get 6. So if you take the cube root of a perfect cube, you're going to get an integer. However, if you take the cube root of a number like 16, look, 16 is not a perfect cube, you're going to get an irrational number. Let me type this into the calculator. All right, so the cube root of 16, look, it's not an integer. There's a decimal expansion that goes on forever and has no pattern. However, if you would take the cube root of a number like 64, 64 is a perfect cube, look, you'll get an integer. So let me go ahead and record that example, the cube root of 16. Oh, I already recorded that, so let me come up with another example. What if we use the cube root of, I don't know, 245? 245 falls between the perfect cube 216 and 343, so 245 is not a perfect cube. So if you take the cube root of 245, you're going to get a number that has a decimal, that goes on forever and has no pattern. So these are all examples of irrational numbers, of numbers that cannot be written as a fraction. All of these numbers over here can be written as a fraction. Now, rational numbers and irrational numbers, those together make up the real number system. Rational numbers and irrational numbers are real. There's, other number systems, for example, the imaginary number system, that would be different than the real number system. But you're going to talk about that in later years.